a control topology for regulating power, voltage, and frequency of PMSG-based wind energy conversion system. Abstract. The global need for cheap environment-friendly energy generation has grown over recent decade due to the depletion of fossil sources. Considering the needs of future generation, renewable sources are the main focus of research work in recent decades. Compared to other sources, wind energy is found to be one of the preferred alternative for many power corporation. But because of the random and erratic nature of wind, some mean of control strategy must be developed in order to extract as much power as possible. Therefore, in this paper, a hill climb search (HCS) algorithm is implemented which can efficiently track the optimum power point at fast varying wind condition and also demonstrates battery connected operation for an independent wind energy conversion system, WECS. The hill climb search algorithm is independent of the wind turbine power speed characteristics and the wind speed, hence it is a sensor-less approach. Here the wind speed is changed in stepwise manner and the maximum power is tracked using the HCS algorithm in SIMULINK-based environment. Thus a variable speed operation is obtained from the permanent magnet synchronous generator, PMSG. Due to variable speed operation and variation of load, due to fault and overload condition, leads to huge oscillation and variation in the grid frequency and voltage waveform. Hence a voltage frequency, VF, controller is designed to bring down the change in voltage and frequency into permissible limit. The VF controller is operated by a voltage source converter, VSC, and hybrid battery storage system. The VF controller regulates the active and reactive power supplied by battery and the generator and controls voltage and frequency fluctuation. In order to verify the proper working of the VF controller, different load disturbances are introduced to the WECS and the voltage and frequency of the three-phase 3-wire connection system are monitored regularly in a MATLAB-based SIMULINK environment. Keywords: MATLAB, WECS, HCS, VSC, VF controller. Introduction. Due to the increasing environmental concern, the old ways of power generation by burning fossil fuel has been substituted by much suitable and environment-friendly renewable sources. Scientists have predicted that there is only a limited amount of fossil fuels in the Earth's crust and it is going to deplete within 30 to 50 years. So, we need to come up with some other viable and more effective alternative which lead to increased focus on renewable sources. Wind energy is safe, inexhaustible, environment-friendly, and is capable of supplying growing energy demand. But, due to the erratic nature of wind, a smart control strategy have to be designed to capture power equivalent to the theoretical limit. Explorations in the field of maximum power from wind conversion system has been a crucial part in transforming wind energy a preferred alternative in energy industry. Energy conversion principle for wind turbine. The energy contained in wind is extracted using the wind turbine blades. As the wind flows, the blade starts rotating. Maximum power point extraction concept. In order to obtain maximum efficiency and for maximum utilization of wind turbine system, it is necessary to extract as much power as can be extractable at any wind speed. This is so because of the erratic nature of wind speed and its seasonal availability. This process of power conversion is ineffective as it leads to wastage of wind energy. There comes the concept of maximum power point tracking, MPPT, which is designed to track the optimum point in power versus speed curve at different wind speed. From the wind turbine power equation, 2, it is clear that maximum power corresponds to maximum. For a particular pitch angle, maximum occurs at a particular tip speed ratio, TSR. Hence, to achieve maximum power at a particular wind speed, rotational speed of turbine must be set at optimum TSR value. For turbines with fixed speed operation, there can only be one optimum point corresponding to a particular speed. Hence, it is not possible to carry out the MPPT operation in fixed speed operation. Whereas in variable speed operation, extraction of maximum power is possible at all wind speed as it will allow the turbine speed variation. Variable speed operations are therefore preferred in most WECS. c:/users/saru/music/00445777.jpg. Voltage and frequency control action. In fixed speed operation there is no need for voltage or frequency control as the generator and grid shares the same frequency. But, in case of variable speed operation, the need for control is inevitable. Due to variable speed operation, the wind generator and grid frequencies are different and any change in load or wind speed can affect the grid voltage and frequency. This leads to a weaker grid, prone to faults and power outage. In order to avoid this, we must design a controller which will damp out the variation in the voltage and frequency. This will confirm a reliable and steady power generation. 2. Wind energy conversion technique. A general wind power conversion system involves a wind turbine, a wind generator and a gearbox arrangement. Therefore different types of available turbines and generators are discussed below. 2.A. Wind turbine. Wind turbine is the first and the most important part of wind energy conversion system. Depending upon the axis of orientation of turbine blades, wind turbines, WT, are classified into two groups. Horizontal axis WT. Vertical axis WT. Horizontal axis wind turbine. As the name suggests, the horizontal axis wind turbine, HOT, blades are placed along the horizontal axis. The general construction of a HOT involves a tower with a flat horizontal base at the top called nacelle. The nacelle mounts the generator and gearbox arrangement. Therefore HOT are mechanically more complex. The gyroscopic action of turbine blade produces stress when yaw mechanism turns to catch the wind. Vertical axis wind turbine. The VAWT needs lower cost of installation and very less maintenance requirement compared to HOT. Another advantage of VAWT is that its operation is independent of the direction of wind speed and it works fine at low wind speed. 2.B. Synchronous generator. The generator has poles as rotor housed on the prime mover carrying a three-phase winding and armature as stator housed inside the body. Depending on type of excitation, synchronous generators are of two types: permanent magnet synchronous generator, PMSG, and wound field synchronous generator, WFSG. Higher power application require WFSG, whereas PMSG is preferred for low power application. The advantages of synchronous generator are: no gearbox requirement. Gearbox involves faults and breakdowns which needs frequent attention. Self-excited. There is no need for external exciter or prime mover. Hence higher power factor and efficiency can be achieved. 3. Voltage frequency control techniques. There are two general types of VF control schemes incorporated in wind energy conversion system. A. Synchronous reference frame theory, SRF. B. Instantaneous current component theory, ICC. C. Svpwm theory. 3.A. Svpwm theory. This technique of VFC evaluates the stator linkage flux and the generator torque by estimating reference DQ axis current values. The dynamic performance of such a system is improved. From the phase current values, DQ axis current values are estimated using Clark and Park transformation theories. The technique used in this control strategy controls the generator torque, speed, and flux linkage in a three-way single approach. The error in speed is fed to pi controller, which gives the generator torque, and the error in torque is fed to another PPI controller whose output gives the phase angle difference between PMSG flux and actual stator flux. From these values of PWM, control signal is achieved using inverse Park's transformation. PWM inverter. The inverter is such a device which is employed to convert DC to AC, and it can also convert AC to DC. It consists of 6 electronic switches connected to boost converter output at one end and 3-phase 3-wire load in the other, see figure 8. It helps in controlling active and reactive power independently. As the reactive power regulates the dynamic voltage, hence the system stability can be improved using PWM inverter. Hence, in order to summarize the benefits of PWM inverters are: it leads to precise control of grid power. Stabilizes the loading of transmission line to its rated thermal limit. Limits the effect of faults between two systems by reducing chance of cascading outage of connected grids. Suitably transmitting from offshore wind farms to AC grids on mainland. Pulse width modulation, PWM, generator. The PWM generator used to generate rectangular pulses for controlling the on/off of the switch. The major advantage of using PWM controller are: the switching power loss is very low, as at switched off condition it takes no current, and during on period power transfer is possible, so there is no voltage drop across the electronic switch. Variable duty cycle can be easily changed, hence it finds its application in most of the digital control circuits. 3.B. Power optimization technique. For power optimization, it is needed to design a control algorithm which is optimized, less complex, and effective. There are 3 major speed control algorithm for variable speed operation. They are: I. Tip speed ratio, TSR. The actual wind speed is calculated using anemometer, and the tip speed ratio corresponding to the value is measured. This TSR value is compared with reference TSR value, the difference of which is fed to the MPPT controller. 2. Power signal feedback, PSF. The optimal power value is calculated from wind generator power versus speed characteristics, which is compared with observed generator power. The error is fed to the MPPT controller. 3. Hill climb surge, HCS. Hill climb search algorithm is a mathematical optimization technique in where the control algorithm continuously tracks the optimum power point of the wind energy power speed characteristics. This method is preferred over other two methods as it does not require the wind energy power speed characteristics, which is not accurate and keeps changing as the rotor ages. See Figure 6. Figure 6. Hill climb search Mppt control strategy. The parameter, duty cycle, voltage, current etc. is measured and compared with optimum value of that parameter star. The error is fed to Mppt controller, which regulates the power converter to optimize the output of WECS. For control methodology and algorithm. I. The implemented Mppt technique. The power from wind generator is fed to a diode bridge rectifier, so we have here. The output of the VFC gives the three-phase reference load current. The difference between load reference and actual load current of the three-phase system is fed to a proportional controller to amplify the error. This amplified error signal is then compared with the triangular high-frequency carrier signal, above 5 kHz, and the gate pulse signal is generated for controlling Pwm inverter. The BSS is used to store energy during high wind speed period when energy generation is more or during low energy demand cycle. Similarly, it supplies the excess energy need during higher load demand. V simulation model and results. In this WECS design, a wind turbine is connected to PMSG whose power is rectified using diode bridge rectifier. The rectified power is then boosted up to the DC link voltage level. The switching of boost converter is controlled with Mppt controller. A battery is connected in the DC link to supply or store the deficit or extra power needed. The DC power is converted to AC using IJERT inverter. The three-phase load is connected to the inverter. Overall WECS model. Figure 10. SIMULINK model of proposed WECS. From the SIMULINK model, it is observed that the WECS consists of a wind turbine, a PMSG, a diode bridge rectifier, a boost converter, a Pwm inverter, a battery storage system, VF controller, filters and load subsystem. VF controller model. Figure 11. SIMULINK model for voltage frequency controller. The VF controller takes nominal voltage, nominal frequency, three-phase load current, terminal voltage, and grid frequency as input. With the help of Pi controller and LPF, it gives load reference currents. The reference frequency is 50 Hz and the reference voltage is 320 V. Mppt control result. 6. Conclusion. From the figures Mppt power versus time plot, it is clearly visible that with Mppt action the generated output power of the PMSG is increased by 20%. This hence shows the fact that without the Mppt action auto-tracking of maximum power is not possible. The action of VF controller to wind change at 2.5 s shows minor disturbances in frequency and terminal power seems to increase after wind change. The battery supplies more power at lower wind speed for speed below rated speed. The output of VF controller to overload shows very low variation in frequency from the reference value, i.e. 50 Hz. From figure it is observed that the terminal voltage of DC link is fixed at its reference value, which is 320 V, and the terminal power is observed to increase after overload, and at the same time battery, which is initially charging up to 3 SEC, starts supplying power. A standalone WECS is designed using power electronic converters and PMSG to extract maximum power at varying wind speed and to balance the effect of voltage and frequency variation due to change in load conditions. We can see from the results of Mppt algorithm on wind generator power output that without Mppt the PMSG power was low, and after implementation of Mppt it has been enhanced. Similarly, from the results of voltage and frequency control the following results are observed, even with nonlinear load. Successful removal of voltage and current harmonics. Load balancing even at faults. Indirect current control action. DC and AC busbar stabilization. Also, the battery-based system, BBS, output at these variable loading is also observed, and it is found that during sudden increase in load the battery starts discharging and during high wind condition it gets charged.